your third web work due on Friday, so that's pretty standard. So it is a little bit different. On Wednesday, we're going to do our first in-class project. And so just as a reminder, so if you go to Blackboard, there is a tab for the project. And you go to the project tab, so there's the first one that we're going to do on Wednesday on cryptography. So it's up to you. If you want to print the slides and bring them with you, you're welcome to, but that's your choice, right? It's kind of like the slides that you normally do for our in-class lectures. But you are required to bring the handout, because the handout has the actual questions on them. So what I'll do is I'll talk a little bit, kind of introduce cryptography and how I use matrices to code and decode messages. And then I'll give you guys time to work on the project in class. So you need to have the handout with you so that you have those questions, so you know what questions you're working on. Hopefully, we'll have time to finish most, if not all of it, in class together on Wednesday. If you don't get fully wrapped up, then you have to Friday, there's one more question or something you have to do or something. So that's what we'll do on Wednesday. We have to do a little bit less work. So today we're going to finish up the inverse of a matrix and talk a little bit about elementary matrices. I doubt we'll get through all of elementary matrices, so we may need a little bit of time on Wednesday to wrap that topic up, and then we'll have the rest of the time to work on the project. So just as a reminder, on Wednesday for that project, just make sure you have that handout with you, so you have the questions in front of you. Cool for Wednesday? All right, good. Okay. Okay, so as I said, we are going to spend a lot of time still on inverses today before we switch gears into elementary matrices. So let's just kind of remind ourselves about how the inverse of a matrix works, right? So we say that a matrix A is invertible or non-singular, right? Invertible or non-singular if there exists some matrix B, so that when you multiply A and B together in either order, you get the identity matrix, right? Now, we said that in order to be invertible, you have to be a square matrix, right? So here we're talking about square matrices. So A and B and I are all n by n square matrices. And we said we think about non-singular being the same thing as invertible, because that means you've got your partner, right? You've got your buddy that you can join forces with to create the identity, right? And our notation here is we would say that B is equal to A inverse, right? Yeah, David.
Is this an if and only if type relation, or is it possible to have a B that creates an inverse matrix, but it's not the inverse?
No, it is not. This is the definition. You can think of it as an if and only if. Yeah. If there's such a B that multiplies by A to give you the identity, then B is the inverse of A. Okay, so what we're going to pick up with today, we've got a lot of little bitty properties that we're going to prove. So there's lots of little proofs here today, just to get down a little bit deeper. One last thing we did say, and then we talked about how we find them, right? So we said, okay, the idea in general, if you want to find the inverse, you would put the matrix A on the left, the identity matrix on the right, and do your row operations until hopefully you can transform A into the identity. And when you do, then the matrix that's sitting on the right now will be A inverse, right? But we said, with the exception of one written homework that I'm torturing with you with, that I'm making you do it the long way, other than that, you're going to use your calculator, right, to find these inverses, because that process is kind of tedious, right? And if you can't do it, right, we saw one where after we did our row reduction, we ended up with a row of zeros in the bottom. And that told us that our matrix was non-invertible, right, that it was singular, that there was no possible way to turn A into the identity, so that particular matrix did not have an inverse. And the last thing we said was that in the case of a 2x2 matrix, those don't use your calculator, because those you have a really quick formula for. It's longer to type it into your calculator than it is to just write down the formula. So we've got a 2x2 matrix that A is invertible if and only if AD minus BC is non-zero. And in that case, our inverse will be 1 over AD minus BC times So remember that A and the D swap places. The B and the C stay put, but they get a negative. So we've got a handy dandy little formula for 2 by 2s. And that's basically where we are at this particular moment on inverse. Any other questions before we start learning some properties? Cool. All right. Okay, so properties of inverse matrices. Okay, so we're going to assume in these 4 properties, and I'm going to peek just so I get them in the same order that they're in the book, that A is an invertible matrix, so A inverse exists. K, so K belongs to the positive integers. Those are also called our natural numbers or our counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so our positive whole numbers. C can be any real number except for 0. And we'll see why it can't be 0 in just a second. And so then the theorem says if all that's the case, then the matrix A inverse, A to the K, the scalar multiple C times A, and A transpose are all invertible. And I'm going to write them up here so we can refer back to them. So the inverse of A inverse, any guesses on what that one's going to be? Just A. Yeah, the inverse of A inverse will just be A. Secondly, if I want the inverse of A to the K, so I've got A multiplied by itself K times, I want to undo all of that. What I need to do is I need to take A inverse and multiply A inverse by itself K times. 3, if I have a scalar multiple of A, and I want to get back to the identity, I'm going to need 1 over C times A inverse. And this is why C had to be a non-zero constant, right, so that we can divide by C. And last but not least, the inverse of A transpose is the transpose of A inverse. Check the camera, make sure y'all can see all those things. Okay. Okay, so let's prove these 4 little properties, okay? Oops, Daisy. So these proofs, especially the first one, is so easy that it's confusing. Sometimes I have the math, right? Things that are so easy, sometimes they're confusing. Right? So if we want to show that 2 matrices are inverses, what we have to do is we have to show that when we multiply them together, we get the identity, right? So to show that the inverse of A inverse is A, we need to show that when we multiply A inverse and A together, we get the identity. But we already know that that's true, right? But we already know that A inverse times A is the identity. So there's actually kind of nothing to say there, just so kind of immediate. All right, so in the second one, we want to show that if I take A and multiply it by itself K times, that the inverse of that is I need A inverse multiplied by itself K times. Okay, let's see. So I've got, on the one hand, I've got A multiplied by itself K times. So there's A to the K. I'm trying to undo all that to get to the identity, right? And so I claim the way that I undo all that to get back to the identity is to multiply by A inverse. K times. All right, my spacing's not great because I really want to write over there, but then I'm not sure. Okay, so the key to this one, because I want to end up with the identity, right? That's how we showed these two things are inverses, and we multiply them together, we get the identity. The key here is that our matrix multiplication is associative. So I can put my parentheses wherever I want, right? If I wanted to, I can multiply these two matrices together first. If I wanted to, I can multiply these two matrices together first. I can start wherever I like, right? I can't move the order, but I can start wherever I like. Well, what happens if I start right here? Right smack dab in the middle. If I multiply these two matrices together first, A times A inverse will give us who? The identity. So then it's like those two pieces disappear, right? And then those two pieces would be side by side. So if I multiply those two pieces, A times A inverse, I get the identity. It just works its way out. So that's the plan. So we're going to use our associativity law, A, dot, dot, dot. And the first place, I'm going to put my parentheses and right smack dab in the middle, grouping A and A inverse together. Right, so that's my associativity of matrix multiplication. And then y'all told me, well, when I do that, those guys become the identity, right? They disappear. So that piece in the middle becomes the identity. Okay, cool. So then I would put my parentheses right there, right? And the same thing happens. They become the identity again, right? And you just keep working your way through it until eventually everything has kind of disappeared and just become the identity. But I still don't want to commit. All right, the third one. All right, so a scalar multiple of A. So we want to show that if we take a scalar multiple of A and we multiply it by 1 over that scalar times A inverse, we multiply those two things together, then we get the identity. Well, remember, I'm not allowed to swap the order of matrices because my matrix multiplication is not commutative. But this isn't a matrix, this is a scalar, right? And I can move a scalar wherever I want, right? So I can move that scalar right out in front. And then, of course, C times 1 over C gives us the number 1. A times A inverse is the identity, and so we get the identity. All right, last but not least, we want to show the inverse of the transpose is the transpose of the inverse. This one's the most interesting, I think. So, observe. I've used the word consider a lot, so I'll pick a different word. So, I want to show that when I multiply those two things together, A transpose times the inverse of A transpose, I don't know how far I need to go down. Again, I want to show that when I multiply those two things together, I get the identity. Okay, so I'm going to kind of do a little scratch flash over here to help us remember some of our properties of the transpose. If I have two matrices, B times C, and I take the transpose of that product, do we remember what we get? C transpose, A transpose, the order flips. All right, I'm allowed to like distribute the transpose, but the order flips. Okay, so here I'm going backwards, right? I have A transpose, A inverse transpose. So when I put them together under a single transpose, the order will flip. So that'll be the transpose of A inverse A. Right? Okay, but A inverse times A is which matrix? The identity. So I have the transpose of the identity. But what is the transpose of the identity? If I flip all those rows and columns, I can't even tell that I did anything. Right? So he is his own transpose. So we're good to go. All right. Okay. So that was property number 1. Here's another one. All right. If A and B are invertible n by n matrices, then their product A times B is also invertible. And the inverse of the product is similar to our transposes in that the order flips, right? So I get B inverse followed by A inverse. All right, so let's prove that. So if I want to show that these two things are inverses, I have to show that when I multiply them together, I get the identity. All right, think for just a second about how you would do this proof, what you would do next. Any suggestions? Yeah, David? Use the associativity property. Who do I want to multiply together first? B and B inverse. Good. So I want to use the fact that my matrix multiplication is associative to regroup and multiply B and B inverse together first. Because what is B times B inverse? It's the identity. So this gives me A times the identity. I'll do this one really slow because I did the other one kind of fast. So B times B inverse gives me the identity. Now, I just made up these parentheses, right? Because, again, associativity, right? So either you can do A times I first or I times A inverse. It doesn't matter because in either way, the I is going to disappear, right? Whatever matrix, whenever you multiply it by the identity just disappears. And then we get A times A inverse, which is, of course, the identity. Maybe I should put a little word here, like as desired. So those two matrices are inverses because when we multiplied them together, we got the identity. Yeah.
I'm not sure if I missed something, but how does their product be the identity prove that they're equal?
Well, they're not. When it proves they're equal, it proves they're inverses. So it would prove that the inverse of AB was B inverse A.
Oh, right. Okay, gotcha.
Does that make sense?
Yeah.
Great question. It takes a little getting used to. All right, we got not one more, we got a couple more. Here's another one. Okay, so we had last week, we were talking about properties of matrix multiplication. I made a really big deal. We did some example where we had two matrices, two products, AC, which was equal to BC, but the matrices A and B were not equal. Yeah, remember that example? We said you have to be really careful because we said we want to think about like dividing by C, but there's no such thing as dividing by a matrix, right? So we're not allowed to do that. So just because these two things are equal, that doesn't guarantee this. Okay, that's true. Okay, but if I know more about this C, in particular, if I know that that C is an invertible matrix, then in that case, I can cancel it because I can multiply on both sides by the inverse. So that's what this theorem says. It says that if C is an invertible matrix, then if AC equals BC, then in that case, I do know that A has to equal B. And the same is true in the other direction. If CA equals CB, and C is invertible, then I know that A has to equal B. All right, we'll prove the first one because the second one is the exact same idea. All right, so what are my assumptions? Suppose that C is invertible. That's my assumption. And all that means is it has an inverse, right? So then there exists some matrix C inverse that C times C inverse is equal to the identity. So that's just the definition of C being invertible. Okay, so now suppose that AC equals BC. Okay, so we've got our invertible matrix. We're assuming that AC equals BC. We're going to try to argue that A has to equal B. So what we're going to do is, whatever you do to one side, you got to do the same thing to the other side. We're going to multiply on both sides of our equation by C inverse. We only can do this because we know that C inverse exists. But now, what's C times C inverse? The identity. I'm going to keep asking that over and over again just to kind of try to get it in your brain. And then A times the identity is A, B times the identity is B. And the other direction works exactly the same way, except instead of multiplying on the right, that's the inverse, you multiply on the left. All right, so here's an example. We haven't done any examples yet. So let's do an example today. Y'all are like, please give us a break from all these proofs. All right, so let's find a matrix X so that A times X is equal to B. All right, so we have the equation AX equals B. And we want to solve for X. So the way with matrices, remember, we're not allowed to divide by a matrix, right? That's not a thing. So the way that we move matrices from one side to the other is by using our inverses, right? So what we can say is that if, and this is a big F, right? If A inverse exists, then where I have my AX equals B, I can multiply on both sides of that equation by A. Again, whatever you do on one side, you have to do on the other side. But then we could solve, right? Because A inverse times A is just the identity. And we would know that X is A inverse times B. Cool. So that's how we can kind of move the A over to the other side, but we're only allowed to do that if A is invertible, right? And I want to make one more remark. Notice, we have to be careful with our matrix multiplication because it's not commutative, right? Whenever I say whatever you do to one side, you got to do to the other side, you have to do it both on the right or both on the left, right? So I multiplied on both sides on the left by A inverse, right? I can't do it on the left over here and on the right over here. That is not how it works, right? So you have to be careful because of that non-commutativity. Does that make sense? You have to maintain the correct side, the same side. The same side, that's the word I want. Okay, so if A inverse exists, then X will be A inverse times B. Well, it's a 2 by 2. All right, so you guys take a second and figure out whether or not you think A inverse exists, and if so, write down what it is. So if you can remember your little formula, look back in your notes if you need to. Your little formula for a 2 by 2. Okay. Okay. So when we do AD minus BC, we get 16 minus 15, which is non-zero, right? So A inverse exists. A inverse is 1 over that value, so I'm going to write it down right here just so you can see that I did it. Right, doesn't really change anything in this problem. So there's my 1 over AD minus BC. A and D swap places. Watch me do it. I did it. And then B and C stay put, but they get a negative. So negative 3 and negative 5. And so X then is this A inverse that we just found. 4, negative 3, negative 5, 4 times B. All right, so let's see what we've got. Oh, let me stop. Everybody okay so far? 4 plus 3 is 7. 12 plus 6 is 18. Minus 20 minus 15 minus 35. Minus 5 minus 4. Minus 15 minus 8. And 25 plus 20. Did I do all that right? Was it okay, everybody? Okay. All right, so there's our X. Cool. So we're allowed to, like I said, to isolate, to move the matrix over to the other side if it's invertible, because then what we're really doing is we're multiplying by the inverse. All right. Okay. Let's do another theorem and proof. We haven't done it in a while. Sorry guys, today is like crazy heavy for a Monday too. A Monday and it's like 4 degrees outside. I'm doing y'all wrong today, making y'all do all these scary stuff. Or maybe you're like, sweet. Okay. Theorem 211 says that invertible matrix, then the system AX equals B has a unique solution, and that unique solution is A inverse times B. Okay, so to prove this, we actually have to prove 2 things, and I'll write that down in just a second. We have to prove that this is a solution to the system, and then we have to prove that it is the only solution to the system. Okay? So there's 2 little pieces happening here. All right, so let's start by writing down our assumptions. All right, so we're going to assume A is an invertible matrix. So assume A is an invertible matrix. We must show that X equal to A inverse B is a solution of the system AX equals B, and that it is the only solution. So there's 2 little arguments we need to make here. We've got to show that it's a solution, and then we've got to show it's the only solution. Okay, so first let's show that it is a solution. So consider letting X equal A inverse times B. All right, so I've got a system AX, and all these X's could have little bars on them if you want them to, because they're technically telling us the B's. They're like column matrices, right, or vectors. Okay, so if I want to show that this is a solution to the system, I've got to show that if I plug this in right here, that I get a true statement. Right? That's how we show it's a solution. We show that we get a true statement. So I'm going to substitute in, for that X, I'm going to substitute in A inverse times B. But when I do that, because of my associativity, I can reassociate, right? And multiply A times A inverse first. And that, of course, is the identity. So I get the identity matrix times B, which is just B. Cool. So we're halfway there. So hence, A inverse B is a solution of the system. Okay, the second half is that uniqueness part, that it's the only solution. So we talked about how we do uniqueness proofs on Friday. Remember the trick? We assume that we have 2 and then show that they're actually the same thing, right? So that's what we're going to do. So we're going to assume that we have another solution. So assume now, I'll call it X1. So assume that X1 is another solution of the system. Right, so we've got our first one, we're calling X, and Now we're assuming we got another one. Okay. So since it is a solution to the system, that means that when I substitute it in for X, I get a true statement, right? I get B. So that's what it means to be a solution of the system. Now, my A, remember, is an invertible matrix. So I'm going to multiply on both sides of my equation on the left by A inverse. But now A inverse times A, that's the identity matrix. So I'm just left with X1 equals A inverse B. Uh-oh. That's what X was, right? So I thought I had found a different solution, but it turns out it was the same solution I had all along, right? So therefore, X equals A inverse B is unique. Okay. So we're going to do some examples. But what this theorem is really telling us is, right, if I start with a system, AX equals B, and I want to solve that system, well, a solution to that system will be A inverse times B. Now, this is one of those things where this is useful to know in theory, but not in practice. And you'll see why in the next example, but not. So you'll see why in the next example why I say that. So a useful idea in theory, not so useful in practice. So let's do a couple of examples. We can see this theorem in action, see what it would look like. Okay, so use an inverse matrix to solve this system. All right. So let me make sure there was a typo that's been corrected. Okay, good. All right, so what's our matrix A? So we have so our coefficient matrix A is 1, -1, -2, 2, -3, -5, -1, 3, 5. So there's our A, right? And so just so everybody's clear about all the other pieces as well, the thing that we called X bar, those would be our unknowns, X, Y, Z. And the thing that we called B, those would be our constant terms, 1, -1, 1. So just so everybody's clear about all those pieces that showed up. Okay, so in example 3, if you look back in this section, in example 3, we already found A inverse. So we're not going to redo it. And A inverse was 0, 1, 1, 5, -3, -1, -3, 2, 1. We already found that. You can look back in your notes and double check. Okay. So the theorem says that if I want my unknowns, my X, Y, Z, I can find them by multiplying A inverse times B. So I take my A inverse, 0, 1, 1, 5, negative 3, negative 1, negative 3, 2, 1, and multiply it by our B, 1, negative 1, 1. That was a positive one. Wait just a second. All right, let's see. So 0, negative 1 plus 1. 5 plus 3 is 8. Minus 1 is 7. Negative 3 minus 2, so that's negative 5 plus 1, looks like negative 4. All right, so that gives us our answer. X is 0, Y has to be 7, and Z has to be negative 4. Okay, so I said a minute ago that this theorem was useful in theory, but not very useful in practice, and here's why. If I gave you this system, and told you to solve it, it would be significantly easier just to plug it into your calculator, right? Hit row reduce, right? And your calculator immediately tell you 0, 7, negative 4, right? That's significantly faster than going through the process of finding this inverse matrix and then multiplying the inverse matrix by B. You get to the same answer in the end. So it's kind of cute in theory to know that such a thing is possible. But in practice, this is a really inefficient way to solve a system, right? It's much faster just to take the system you've been given and row reduce and be done with it. Cool. Okay, so I want to do one more because we're going to make, I want to make a point. Notice here, right, that we got a unique solution. Okay, that's important. Stick that in your brain for a minute, a couple minutes from now. Okay, same system. The only difference is our constant terms are all 0. Cool. Everything else is the same. The only thing that changed is the constant terms. So how is that going to change? Well, what will I get? When I multiply my A inverse times all zeros, what am I going to get as my answer? All zeros, right? Cool. So if I have an invertible coefficient matrix, remember what this kind of system is called? Starts with an H. Homogeneous. So all the 0 terms are homogeneous. Then in that case, the only answer I can possibly get is that trivial solution where all of my unknowns are 0. Cool. Okay, so that leads us to the beginning of the biggest theorem in the entire course. And I call this theorem the Big Hammer Theorem. So let me tell you what it says, and then I'll unpack why in the world I call it the Big Hammer Theorem. Okay, so the Big Hammer Theorem says that the following are equivalent. And in math, that's often abbreviated TAE. So sometimes you'll see that abbreviation. The following are equivalent. Okay, so let's write them down, then we'll unpack them. Number 1, A is invertible. Number 2, A is row equivalent to the identity. A is row equivalent to the identity. Number 3, AX equals 0, the homogeneous system has only the trivial solution. Number 4. AX equals B has a unique solution for every B in RDA. And finally, 5, AX equals B is system for every B in RDA. So I'll let you write those down for just a second, and then we'll chat about what all that means. Math does not want to stay on my ear today. Okay. All right, so what are all these things saying? Okay, when we say the following are equivalent, that means either all of these are true about a matrix or none of them are true. So if we know that one of these statements is true, then we know that we automatically get all the rest of them, right? Or if we happen to know that one of them is false, then we automatically know that all the rest of them are false. Do they all hold or none of them hold? Cool. All right, let's see if we believe them. Okay. So if A is invertible, right, then we know that's the same thing as it being row equivalent to the identity, because that's how we find the inverse, right? We start off with A and I, and if we're lucky, we can transform A into the identity matrix, right? So if A is invertible, it's got to be that it can row reduce down to the identity matrix. That's how we find the inverses, right? This third one, that's the one we just did, right? We said, look, if A inverse exists, and I want to solve a system, and it's a homogeneous system, then the only answer I can possibly get is the trivial solution, right? The one right before that I told you to tuck away in your brain, right? We had the non-homogeneous system, right? We got a unique solution, right? That if A was invertible and I go to solve, I just get one single unique solution. And then consistent just means I've got a solution, right? So all these things are kind of coming together. So either all of these statements are true or none of these statements are true. Now, this is the most important theorem in the entire course. And we're going to add on to this theorem as we go through the course. So by the end, we'll have something like 20 statements on this list. And on every single exam, I'm going to ask you, state X number of things that are equivalent to A being invertible. And so, of course, on the first exam, maybe I'll ask you to name 4, because we'll have a couple more down here. We'll have 6 and 7 by next week, right? So maybe I'll ask you to name 4 of them. On the next exam, the list will be longer, so maybe I'll ask you to give me 6. On the final exam, maybe I'll ask you to give me 10, because you'll have 20 to choose from, right? So every exam, I'm going to ask you, give me statements that are equivalent to A being invertible, because it's the most important theorem in the course. Now, the reason why I call it the Big Hammer Theorem is for 2 reasons. Number 1 is it's the most important theorem in the course, and it doesn't have a name, which is really unfortunate. So I gave it, I was like, it's got to have a name. So I just named it the Big Hammer Theorem. I'll tell you why I picked that name in just a second. So as far as this course goes, on homework, on your exams, if you're using this guy and you want to call it the Big Hammer Theorem, feel free. I'm going to know exactly what you mean. But if you leave this room, now Dr. Pines knows that I do this, so you can say to Dr. Pines and he'll know what you mean too. But if you go off to grad school or something somewhere, right, and you start talking about the Big Hammer Theorem, people are not going to have any clue what you're talking about, because Dr. Heller is the one who came up with that name and no one else knows anything about this, right? Although I did have a student, Jack Ryan, who went to grad school at the University of Tennessee, and he took it with him to the University of Tennessee. So I'm like, sweet, it's like growing. But anyway, so they might know that it's the Big Hammer Theorem if you go to the University of Tennessee. The other reason why I call it the Big Hammer Theorem, why I picked that as the name, so it's partially in honor of one of my grandfathers. So he was a wonderful man who had lots of talent, but being handy around the house was not one of them. And so the joke with my grandfather was, if anything was ever wrong ever, the only way he knew to fix it was he would say, I'm going to go get my big hammer. It didn't matter what tool was actually appropriate for the job. My grandfather was going to get his big hammer. And there was this story about when my dad was a little boy, their Christmas tree was like leaning. They couldn't get it to like stand up straight. He literally got his hammer and nailed the damn thing to the floor, like their actual floor of their house, to try to get the thing to stand up straight. Patience also not a tribute of the Hellers. Anyway, so I kind of said that. So there are going to be things that we're going to use this theorem for on down the line, where it's going to be like, really, we just need something small. But instead of using a small thing to do the thing we need, we're going to pull out the biggest hammer we've got and just like smash it into oblivion. Like, we just kind of need this one little result, and rather than doing it small, we're going to be like, heck with that. Here's our huge hammer, and we're just going to, like, crush it. Cool? So that's another reason why I call it the Big Hammer Theorem. Feels like we're pulling out way heavy machinery for just a little bitty task. But that's what we're going to do on down the line. The beginning of the Big Hammer Theorem, it will be with us now until the end of the course. Cool? Any questions, Sophie?
Hey, Dr. Heller.
Yeah. So great question. If a theorem has a name, we haven't learned any yet, I don't think, that have a name. If it has a name, you can reference it by name. And this one you can call the Big Hammer Theorem if you want. I'll know what you mean. When it comes to the properties, like, oh, AB transpose is B transpose, A transpose, I'm just going to, you would just, in your notes, you'll just say, like, because AB transpose is B transpose, A transpose. But I do not expect you to memorize its theorem 2.6, part 4, blah, blah, blah. I do not expect you to memorize the numbers and all that kind of stuff. So you know what they say, but you don't need to know what number of theorem it is in the book. Does that help? Okay, yeah. Yeah, is there a question online?
Yeah, so 2 questions. First was, what was the question that was just asked? We couldn't hear what it was.
Okay, so the question that was just asked was, in proofs on the exam, how do I want you guys to reference other theorems? So do I want you to say, like, oh, from theorem 2.6 part 2, the answer is no. I do not want you to know them by name, by number. I just want you to know what the properties say, and you can just refer to the property itself that you're using on the exam.
Okay, and great. And the second question was for 4 and 5. Why is it for every b in r to the n? Like, why is all real numbers to the n power or whatever?
Okay, so the b's, and I should have said up here that A was an n by n matrix. Let A be n by n. That's where the n comes from, right? So in this example, right, A was a 3 by 3. This is A inverse, right? But A was also 3 by 3. And so the B's, right, then were vectors that live in R3. So that's just the appropriate size so that your matrix multiplication makes sense, right? So if A, and then also A inverse, is n by n, and you're going to multiply it by one of these column vectors, in order for that matrix multiplication to be defined, B has to be an n by 1. So B has to live in Rn. And so this, the Big Hammer Theorem is saying that these types of systems, this AX equals B, has a solution for every single B in the whole wide world, right? So if A is not invertible, right? So if A is not invertible, what that would tell you is there's at least one B out there, so that AX equals B does not have a solution. right? And there's at least one B out there such that AX equals B maybe has infinitely many solutions, right? But if your A is invertible, then for every B, every one of these column vectors you can write down in the whole wide world, you're guaranteed to have a unique solution. And we know what it is. It's A inverse B. Does that help?
Yes, thank you.
First, like, it helped me. Okay. Okay, two more. So the proofs that we have done today, we've done a lot of them today, but they're all kind of theory things that I may tell you ahead of time are fair game for the exam, but not things that I would expect you to be able to kind of come up with on your own necessarily in homework. So I want to take a minute and do a couple of proofs that are maybe more the speed of what you would see in your homework so you get a feel for what those might look like. Okay, so the first one is this. Prove that if A squared equals A, then I minus 2A is its own inverse. All right, so prove that if A squared equals A, then I minus 2A is its own inverse. So here's our proof. We want to start our proof with the word proof. And let's write down our assumption, which is that A squared equals A. Okay, so if I want to show that this matrix is its own inverse, what that means is that when I multiply them together, I have to get the identity, right? So consider, I want to show that if I multiply I minus 2A times itself, that I end up with the identity. Okay, so let's see what happens, right? So it's sort of like foiling. I know I'm not supposed to say the word foil, but we're going to multiply these pieces out, right? So if I multiply, well, I'll just do it slow. So I have I times I, and then minus 2 times I times A, and then minus 2 times A times I, and then plus 4 times A times A. Think of it just kind of multiplying all those little pieces out, right? Okay, so if I multiply the identity by itself, what do I get? The identity. All right, minus. All right, I times A is just A. A times I is also just A. And then I would technically get 4A squared. Okay, so I have I minus 4A. And then my assumption is that A squared is equal to A. So 4A squared is the same thing as 4A. So that is because A squared equals A, right? And now I'm in business, because minus 4A plus 4A give me the identity. And so, hence, I minus 2A inverse is I minus 2A. All right, one more like this. Prove that if A squared equals A, then either A is the identity or A is singular. All right, so prove that if A squared equals A, then either A is the identity or A is singular. Okay, so what's our assumption? We're assuming that A squared equals A. So let's start with that. Okay, now, so we got to show, right, either A is the identity or A is singular. Okay, so we have a choice with A. So either, see if you believe me, either A is singular or A is non-singular. Right, either it is invertible or it's not. Right, that's true of every matrix. If it is singular, then we're done. So if A is singular, then we are done. Nothing to do. So assume that A is non-singular. In which case we've got to show it's the identity. Okay, so non-singular means you are invertible, right? So then there exists a matrix A inverse so that A times A inverse and A inverse times A both yield the identity. So that's just the definition of A being non-singular. Okay, I have not yet used this assumption, so let's do that. All right. So we know A squared equals A. I want to get an A inverse in the mix. So I'm going to multiply both sides by A inverse. So multiply both sides by A inverse. Okay. What survives on the left? Just A, right? A inverse A gives me the identity, so I get A. What survives on the right? The identity. But that's exactly what we wanted to show, right? If it's singular, we're done. If it's non-singular, it has to be the identity. So a little concluding sentence, hence, A is either singular or is equal to the identity. Any questions? Okay, I do want to go ahead and start 2.4 because I want to get through as much as we can so that we have as much time as we can for the project on whatever day that is. So we can at least define elementary matrices to kind of get a feel for them. Okay, it's a short section. All right, so think of back. Week 1, we've got a matrix. We're going to perform a row operation on it to put it in row echelon form or reduced row echelon form. What are the 3 things we're allowed to do to that matrix? What's one of the 3 things we're allowed to do to that matrix? Multiply by a non-zero scalar. What else am I allowed to do? Yeah, go swap two rows. What's the last thing I'm allowed to do? Add a multiple of one row to another row, right? Okay, interchange two rows, multiply a row by a non-zero constant, add a multiple of one row to another row. Okay, so here's our definition. An n by n, so it has to be square. An n by n matrix is called an elementary matrix when it can be obtained from the identity matrix by a single elementary row operation. So we start with the identity, we do one of these things to it, and now we have an elementary matrix. Cool. Okay, so let's look at some examples and figure out which of the following matrices are elementary. All right, so what do you think? Can I start with the identity matrix, do one of those things to it, and end up with this guy? Yeah. What would I do? Yeah. Exactly. We multiplied row 3 by 5. Cool. So yes, this is an elementary matrix, right? We multiplied row 3 by 5. Okay. All right. Can this be an elementary matrix? No, because it's not square, right? So it's not even running, right? So no, it's not a square matrix. Right? This bottom one, is this an elementary matrix? What do we think? Yes. If I multiply row 1 by 4 and then add it to row 3, I get this guy. Cool. So yes. So we added 4 times row 1 to row 3. So that is an elementary matrix. All right. What about this guy? No, because I would have to multiply by 0, right? And the rule is you have to multiply by a non-zero constant, right? So no, can't multiply by 0. Okay. Is this an elementary matrix? Yes, right? I swapped row 1 and row 2, right? So yes. We swapped row 1 and row 2. Okay. Last but not least, is this an elementary matrix? This was a little bit tricky. The answer is this one was, right? I multiplied row 3 by 5. Here, I would like to multiply row 1 by 2 and multiply row 2 by 3. It takes 2 operations to get to this guy, and that's not allowed. That's too many. Okay? So no, because this requires 2 row operations. No, because it requires 2. And to be an elementary matrix, you've got to be able to get there from the identity matrix with just one single row operation. Cool? All right. Okay. So we'll pick up more of these. I'm not trying to pick up stuff. So we'll pick up more of these on Wednesday. Have that handout because we should have time to go ahead and get to the project and stuff. Cool? And you do have your second homework due on Wednesday, so just don't forget. Stay warm. It's going to be a chilly week. Go back to the definition. Yep. You're welcome. Yeah.
I have a really quick question about the previous slide.
Sure.